Welcome, ladies and gentlemen, to another exciting episode of Dave Does Math from Home. We got a really quick one for you today. Section 8.1 is titled Basic Integration Techniques, and it's a little bit weird. I am pretty sure that the author of this textbook sort of expected everyone to go through it in order, and we are not doing that. We are skipping the entirety of Chapter 7. I don't remember what it's about, but we're skipping the whole thing, and we're going straight into from chapter 6 to chapter 8. So I think that section 8.1 was written as like a review to get people back into this integration mindset after whatever happened in chapter 7 was happening. We kind of don't need that review. So most of this is going to be exactly the same as what we've been doing for the last 2 weeks. We're not rotating volumes anymore or we're not rotating regions anymore to get volumes. But it's the integration techniques we're talking about are the same thing we did in chapter 5. Because of that, I'm often tempted to just skip section 8.1 entirely, but there are two relatively small but new pieces of information that happen in section 8.1 that make it worthwhile to talk about briefly. So this won't be a long video. We're definitely only doing one part to this. There won't be multiple parts of this video. Just the one. And so let's get right into it. Basic integration techniques include all of the standard antiderivative stuff we've already done. Like, we already know that the antiderivative of x to the n is x to the n plus 1 over n plus 1, as long as n does not equal -1, that sort of thing. Like, we already know that. We know the antiderivative of sine, cosine. And we can do antiderivatives of things like x cubed sine of x to the 4th. This is an inside-outside other problem, or the official name for these is integration by substitution. I call them inside-outside other problems. The inside is x to the 4th. The outside is the sine of something. The other is x cubed dx. So we set w equal to x to the 4th. We find the derivative of that. It's 4x cubed dx. These things almost match. We can make them match if we put a 4 in here and a 1/4 on the outside to balance. Now they match perfectly. And I can substitute this for 1/4 the integral of sine of w dw. And of course, the integral of sine is negative cosine plus c, and then we unsubstitute. So we get negative 1/4 cosine x to the 4th plus c. So this is the part that's just review. I want to go from here into one of the small things that this section is trying to introduce, and that is the idea of skipping a lot of steps when we do linear substitutions. So for that, I want to talk about something like I want to get a new marker. That one's not doing so hot. I want to talk about the integral of e to the 6x dx. Technically, because this isn't just an x, what we have here is an inside and an outside and an other. But the other is just dx. Inside is linear, and the outside is whatever it is, e to the something. So for these kinds of problems, instead of doing the entire routine where we're making a w and we're setting it equal to the inside and we're finding its derivative and then we're adjusting things. You can even skip the parts where you write all this down. If your substitution is linear, then it should be pretty clear that what you need is a 6 here and a 1/6 on the outside. And then you can kind of just integrate this like normal. Like, the 1/6 stays on the outside, this is e to the 6x plus c. So, practicing, we just did a sine, let's do a cosine. Practicing these integrals, these linear substitution integrals really quickly without going through the whole process is going to be very useful for us in the coming sections. When we start doing integration by parts, finding these things really quick is going to be important. So this is a useful skill. Just whatever this is, we know the integral of cosine. The integral of cosine is sine. The blob never changes. If you've got a -4 here, you put a -4 on the outside, toss a c at the end, you're done. If you want to do the integral of 3x minus 12 to the 11th power. We know that things to the 11th power will integrate into things to the 12th power. 3x minus 12. Oh, I should use a different number here. Let me make this into 9, so it's different from this. Okay. 3x minus 9 to the 11th is going to integrate to 3x minus 9 to the 12th over 12. But because you have a 3 out front, you're going to put a negative, or you're going to put a 1/3 here. So if you simplify this, you get 36 on the bottom. So that's one of the things I want you to think about as you're doing this homework assignment, is when you see these linear substitutions, try to skip steps. Don't do the full inside-outside other W, DW balance. See if you can skip, see how much of that you can skip so that you can just go straight from this to an antiderivative. We could do a natural log one as well. If I want the integral of 1 over 7x plus 3 dx, the integral of 1 over things is the natural log of those things, 7x plus 3, but I'm going to attach a 1/7 to this because of the linear substitution. So, that is technique number 1, doing linear substitutions quickly while skipping steps. This doesn't work for nonlinear substitutions. I mean, like, if you do integration by substitution enough, you can start to shortcut some of the nonlinear substitutions, and those will get easy, more straightforward for you, I'm sure. But they're slightly more complex. So just be careful about doing those substitutions. The other technique that we're going to talk about, the other like new piece of information we're going to talk about here, is called the half angle formula, and it will allow us to, God, all my markers are dying today. Let's try this one. The half angle formula will allow us to integrate things that look like this. This is kind of a problem for us because this, as written, is a composite function. We have an inside and an outside. The inside is sine, the outside is something is squared. If we try to do this by substitution, we're going to have a problem. We have our inside and our outside. Our other is just dx. But because the inside is sine, we would set that to w. dw would be cosine. We don't have a cosine in here to use as part of that substitution. If this was sine squared cosine dx, or sine squared x times cosine dx, then we could use integration by substitution to solve this. But that's not what this is. This is a sine squared without the cosine. So to do this, we're going to use a trig identity called the half angle formula, which lets us replace sine squareds or cosine squareds with other things. And I'm 99% sure I remember what the half angle formula for sine is. Usually I just look it up. Like, it's easy to, you can Google half angle formula for sine. I'm pretty sure the half angle formula for sine is 1 minus the cosine of 2x over 2. And I think the half angle formula for cosine squared is 1 plus cosine 2x over 2. I'm pretty sure this is it. I'm going to go look this up real fast so that I can be perfectly confident that I'm not lying to you. Yes! 30-second Google of half angle formulas has confirmed that this is correct. Sine squared, they both turn into 1 cosine 2x over 2. Sine uses a negative sign, cosine uses a plus sign. So, these are the half angle formulas, and these will let us integrate this stuff really quickly. So we can pull this over 2, we can pull outside. So we just have 1 minus the cosine of 2x dx. And now we get to put our linear substitution go fast training to use. 1/2 from the outside will stay there. And this is the integral of 1 is x. The integral of negative cosine 2x is minus the sine of 2x over 2. And we'll toss a c at the end of that. So this is the integral of sine squared using the half angle formula for sine. And this, you can imagine, is almost exactly the same. We'll pull the 1/2 out in front, not that symbol. We'll pull the 1/2 out in front so that we're integrating 1 plus the cosine of 2x dx. And then the integral is x plus the sine of 2x over 2 plus c. That is all of the new stuff that we need to talk about in section 8.1. The rest is all just review of stuff you already know how to do. So that's it.